spline-driven flow maps. So this is going to be the showcase and technical breakdown of my tool to make spline-driven flow maps. So what is this all about? As you might expect already, this is all about creating flowing effects using splines. So we have this spline on top of our surface, and this spline is what drives the full effect of the flowing lava around. Which is amazing because we can take the spline and start moving its points, and we can see how it refreshes, how it updates the path immediately after. Super important to make fast and quick iteration. So yes, we are going to learn all the basics behind this tool. So we are going to divide this video into 3 sections. Basically, the first one, right after this introduction, is going to be just a general showcase of the different possibilities with the tool, different crazy applications of it, the settings, the different ways to play with it basically. After that, we are going to talk about a technique called flow maps. So this tool uses behind a technique, a pretty standard common technique called flow maps, which on its most common shape, it consists in storing the information about a path inside of a texture and then use that texture inside of a shader to extract that information back and use that direction information to push our UVs along a path. So that way, when we use those UVs to sample another texture like lava or slime or water, it gives the illusion that it flows along that path. However, the flow map technique on its basic version uses textures as method to transfer this flow data to the shader. We are going to see how we are doing this thing a bit different because we are not using textures at all. We are actually saving and storing all this data in the geometry itself, but we are going to talk more about that in a bit. Once we have the full context, we are going to come back to the tool and we are going to see the full breakdown, the full technical breakdown. We are going to literally learn how every single step behind is made. So at the end of this video, you will not only have the full context about the flow map technique, but also you will be able to do your own implementation of spline-driven flow maps. Let's begin. Okay, here's the demonstration. What do we have here? We have a plane and we are going to convert this plane in one of our fancy lava flow maps. What we have to do is first assign a material to it. So we are going to go to the materials, of course selecting our surface, our plane, okay, it's just a plane, and add the material for the lava, which is already prepared to read the data that is procedurally generated regarding the flow from our tool. And of course, we are going to see how that is received by the shader later in the theory section. But for now, let's assume that the data is going to be delivered from the tool to the shader. Now, let's focus first in the actual tool per se. So if we select the plane and go to the modifier sections, and add a new modifier, a new geometry node, and then we look for geometry node underscore spline underscore flow map, which is my tool, and also I have another version which is a bit more simple, but for now we are going to use the other one. Now we have this. And what is this? Basically we have a few fields to play with it. First of all, this is all about splines, so meaning that we need some splines. We have them here. Okay, we have these splines here, right? I'm going to isolate it to visualize them better. And these splines live under this collection. Perfect. So now what we have to do is to go back to the plane, go to the spline collection section, and just drag and drop the collection where our splines are. Nothing happens yet, right? But it's better to start enabling the material. So nothing is happening there, but then we can play with the surface subdivision value. Let's enable the wireframe and let's see what happens when we start incrementing this value. The more subdivisions we add, the more accurate our flow map is. However, it is a bit nasty yet, right? It breaks here. It's too much. It's too heavy. So we need to tune it a bit. For that, let's play with the intensity. And actually, you know what? I'm going to reduce this subdivision just a bit to 7. Now let's play with the intensity. The intensity, you know what? I think that is fine in 1, but if we reduce this like to 0.3, now everything is more smooth, more calm. That's why I think that 1 was actually a good value for it. Because what is wrong in this example is not the intensity, it's the thickness. So let's just play with the thickness instead. What if we just reduce this value to, I don't know, can be 0.5 maybe? The thing is that the more and more that we reduce it, it started making more sense. It looks more natural. We can increase it, decrease it, increase it, decrease it. Actually, you know what? I like it in 0.45. Perfect. Now we can play with the blur. What is the blur? Well, the blur will help us to smooth the flow on the parts that it merges with other splines. So for example, let's say that here where these two splines, this and this one, merge, basically the intersection between this spline. Let's say that we don't have the smooth effect there. Let's reduce the flow blur to 0. Now you see how everything, like, it's a bit harder. It's not bad, but the way that the flow splits in this part is a bit aggressive. Also the way that it separates, like, between the rock and the lava is super hard. Probably not desirable. So that's why we have also a blur option, which I think that is probably nice on its original value, that is 10. Okay, so let's keep it as it is. We are almost there, but also we can play with the directions of the flow, because for example, if you take the splines and go to edit mode, select all the vertices and then go to right click and switch the direction, now the flow is going to switch for that spline only. Okay, which is great because probably you want that. But a nice thing is that you can invert the general flow of the entire thing by just clicking on the flow invert direction toggle. So if you click on it, you can see how the overall flow just flips. Let's see it while we play the animation. So flipped, original, flipped, original. Finally, the other property that we have is attribute for the shader. We already said that all this data of the flow is going to be sent to the shader, and the shader is going to use this data to push the UVs of these textures and etc. That's the other story that we are going to see in a bit. But for now, we can trust that, we can understand that this data is going to be sent to the shader as geometry attributes, meaning that every vertex here actually contains data about the path. Every vertex here knows on which direction its UVs should move. And even though this attribute is injected like in a default way to the material, and that is what is happening for this example, we can also specify a custom name. So for example, I can come here and tell it, you know what, my flow data is going to be called lava flow. Nothing stops you to do that. But for this case, we are going to use the default attribute. Perfect, but something is missing. Something is missing, and is what about the tessellation? Well, not the tessellation, sorry, the actual vertex offset, the movement, the fluctuation of the geometry, because right now everything is flat. What happened with the fancy movement? Well, actually, that is, if you think about it, that is lava specific, because if we were doing like water or slime, probably that offset would be way different, or probably we don't even need it. So what I end up doing is that I didn't include that offset in the tool per se. Instead, I separated that into a different geometry node modifier. That is this one. We just go to the, let's stop this. We just go to the modifier section, go to geometry nodes, and just look for lava deformation. What it does is that these geometry nodes, which we are going to see at the end in the breakdown, receives also the data from the flow map that is written by the previous modifier. And that way we have the full illusion. So before continuing with the theory, let's just finishing looking some of the examples. So here we have something more interesting, that is this thing. And why is it interesting? Not only because of the shape, it is because we are talking about flow maps that flow in the texture space. They flow in the UV space. But if you are like clever, you will notice that the splines don't live in the 2D space. Splines are actually world spacing. They have 3D coordinates. So an interesting thing that is happening here is that every vertex from this geometry is actually grabbing the direction from the spline, but is translating that direction into something that we call tangent space. Is converting the directions from 3D space from the splines into 2D space, into 2D UV space. And that conversion, even though it's not a super complex thing, is interesting because without that, we would not be able to do this kind of things. And otherwise, this tool would only work in planes. So that's the interesting part of it. So I think that now we are ready to actually get into the logic, and we are going to come back to the tool after to see the rest of the breakdown, basically starting with the technical breakdown. So in order to understand the basics behind the flow map technique, we have to remember how to do the most basic flowing effect possible with UVs. In this case, it's of course taking our UVs and adding some value on one of both axes, like x-axis or y-axis, and that causes, of course, that whatever texture we sample with it is going to move horizontally or vertically. Very simple stuff. But if we need a bit more of directionality, we can also rely in something a bit more like a bit more clever. Like we can split literally the geometry of a river, for example, into two paths. As long as we unfold the UVs in a way that they end up straight, and aligned in a certain axis, as we see on the left side, we will be able to do exactly the same thing, moving the UVs in a certain axis to achieve a flowing effect. Very simple stuff that probably everybody knows. But what if we need a bit more of control? What you are seeing here in the background is actually a web tool, which link I'm putting in the left bottom corner. We are not using this tool actually for this project, but the resource is there. So you can access to it and start playing with it. So even though we haven't explained what a flow map is exactly yet, by seeing this, you can already realize or notice that this is all about defining a path and using that path to push a texture along it, right? So let's define what a flow map is. A flow map is actually a technique that allows us to store the information about a path inside of a texture. And then we can inject this texture inside of a shader to extract all this information and use it to move the UVs along that path. So even though we haven't explained what all these greenish orange colors from the flow map mean, we can assume that they mean directionality in some way. So let's see some basics. To understand where the colors of a flow map texture come, we need to remember that a vector can be a color. What I mean is that vectors can be represented as colors because vectors are composed of two components, x and y, in the same way as colors. And vectors are directions. Therefore, if we want to store the information about the direction along a path, we need to store it as colors in a texture, because of course textures only accept colors. What else we can write in a texture if it's not a color, right? So if you notice, if you look at the right side and see this flow map, you will see a lot of gradient colors going from the reds, shifting to the yellow, shifting to the green, going back to some kind of brown, and back to the red again. So if you are clever, you already assume that these colors are the combination of different values depending on the direction that is stored as a color, right? Because of course we are representing the components of our directions, the components x and y of our directions, as the components red and green of the color. Okay, but all this path basically only has movement around this circle, but not in the middle and not in the corners. So if that's the case, so why the texture has all these yellowish tonalities in the middle of the circle and in the corners? Shouldn't that be like black? Because if we are talking about something that doesn't move, that means that it should have a value of 0, and that means that it should be black, right? Well, that idea is more or less correct, but the thing is that we cannot store a vector as a color directly. We need to do something else before. And that explains why we have these yellowish tonalities in the zones that don't move at all. So when storing a vector, in other words a direction, as a color, we have a big problem, and is that we cannot store negative numbers. So if we have this direction that goes around 360, basically all the directions that fall into these quadrants cannot be represented as colors. Why? Because colors only accept positive values from 0 to 1. At least the common textures that we are used to use, right? So this means that if we want to store a direction that points in any direction, in any 360 freedom angle, we need to do something else. What if we just take all this coordinate space and just compress it? We just take it and stretch it. Well, not stretch it, the opposite. We compress it and send it to this space. If we do this, then we can actually store it as a color, because now this arrow no matter which direction it takes, it is always inside of the range of 0 to 1 positive numbers. But the difference is that, of course, the arrow needs to be tinier in order to fit into this space, and also there is another important difference, that is that the arrow is no longer on the origin, is no longer at 0, 0. Instead of that, we are going to pretend that our new origin is the coordinate 0.5 in the x and the y axis. Which is no problem at all. We can still understand the direction, right? We can do some math there in the shader later to restore the actual direction. As long as we can restore it and save it in a texture, it's fine. And that's the only purpose of doing that. So if you notice and you grab a color picker, for example, and type 0.5 in the x and y axis, in other words, in the red and green components, you will get this characteristic yellowish tonality of a flow map on the zones that have no movement at all. And just a final thing, these two spaces can be named as you want. Basically, it's just a very trivial operation, it doesn't matter. But a common way to name it, or a practical way to name it, is full range, for the full range from -1 to 1, or pack, because it's literally the same space but all compressed in a different space. So the operation that we need to do in order to achieve this is to multiply our vector, our original direction, by 0.5. Why? Because we need to make it shorter, we need to make it tinier in order to fit in the new space. And then we have to add 0.5 in both axes to move it to the new origin, to the new fake origin, that is 0.5, 0.5. So that being said, now we can summarize the directions of a flow map with this chart. Basically, this chart will help us to do two things. First of all, it's just a guide for us when we are working with flow maps, because sometimes things might become a bit tricky. So it's very helpful to have this chart all the time, so we can do very quick confirmations that we are doing the things in the right way. Here we have just 8 different angles, 8 different possible directions with their proper or corresponding R and G values matching that direction. And of course, in the middle we have the fake origin, our no movement zone, which is 0.5. So here we can compare our chart with the colors that this arrow adopts when it starts rotating around the 360 axis, inside of the packed space, of course. But are we sure that these values are correct? Are we sure that, for example, the right direction should be 1 and 0.5 in the red and green channels? The orange, I mean? Or are we very sure that the diagonal direction upwards and to the right is 0.85, 0.85? Because they might look a bit strange, right? Who ensures that these values are correct? Well, they are correct, and we can confirm that very easily if we open any math plotter out there. For example, in this case, I'm using Desmos on the right side, and I just add a point. I make it to rotate around the new fake center, which is 0.5, 0.5, and I just print out its coordinates. This way I can stop it at any point and actually confirm that the values that it adopts on the X and Y axis are actually what we have in the chart. So this is only one way to confirm that we are actually developing this logic correctly. So we are going to jump into Blender as we said, but we are going to see some resources first. First of all, this technique is very pretty because it doesn't matter how you create the flow map, the concepts are the same, directions stored as colors. This means that nothing stops you to literally paint this by hand in any paint edition or image edition program, like GIMP for example. Also, Out there is plenty of add-ons. You can actually download add-ons that do these flow maps already for Blender, for example, by painting, by literally using a brush, things like that. Unfortunately, this add-on that I'm showing in the middle is deprecated for the latest versions of Blender, but it's known that the creator is working on it. Or the third way is to do it yourself procedurally using geometry nodes or similar. Or you can use Houdini or do it inside of a game engine, inside of Unreal, whatever. So this is the pretty part of the flow maps, that it doesn't matter how you create the actual data as long as it follows the convention of storing directions as colors. So before continuing, I'm going to show you something very quick, and is how to create a flow map by hand, because even though we are not going to use this for real, because it's super tedious, it's important to understand the principles. So for example, here I have this canvas all in this yellowish tonality, which matches our no movement zone in the chart, which is basically the color of 0.5.5. If we go to the color picker and we want to set it up as no movement, we need to come to the chart, see the color, which is 0.5 in R and G, and just set that here. In this case, GIMP accepts values from 0 to 100, but it's exactly the same. So 0.5 translates to 50. And of course, in the blue channel, we set nothing because we are talking about 2D coordinates and we don't care about the Z-axis, which would be B. So with that, we can just paint the full background with it, meaning that this flow map is not moving yet. Now, if we want to paint an actual direction, the only thing that we have to do is to select the brush, see our chart, look at our chart, and say, okay, I want to move to the right. So you localize the right color, the orange, and set it here. So it's 100 for 1 and 50 for 0.5. So this is 100, this is 50. And on blue, of course, nothing. And now we are ready to paint. Oh, sorry. We're ready to paint a bit of path, right? Then let's say that we want to paint in direction downwards. So we come back to the color picker. We do the same. We localize the color in the chart. In this case, it's 50 and 0. And we start painting down. And of course, I'm not going to continue because this is a very nasty, ugly process and very tedious and slow. However, in GIMP, fortunately, there is a better way, and is that if you pick a brush and enable the dynamics and go to the gradient options and create your own custom gradient, and then in the custom gradient you define 8 different sections that match the 8 different sections of the chart, and then assign the same exact colors as the chart, you will be able to paint the flow map automatically. Of course, there is an extra step, that is going here to the paint dynamic editor and just tell the brush to use the direction as color by checking this box. This way, whenever you start painting, it's going to translate the angle on which you are painting on into one of these positions in the gradient matching your chart, starting from the left in direction counterwise, passing through this brown, then through the reds, then through the orange, yellow and greens again. So we can paint very crazy things here. Actually, we can confirm that is right by painting from left to right, and we have orange from right to left, and we have green, etc. And we have all the different directions that we defined in our chart. Sometimes it's a bit buggy, but that's another story. It works. So yeah, we are ready to see the next part, which is the shader. Okay, now we are going to see how to read the flow map inside of a shader to apply the effect over our UVs. What I have here is a flow map already imported into Blender. Remember that you can generate this flow map as you want, in Paint if you want, manually if you want, it doesn't matter as long as the data respects the theory that we just discussed before. Anyways, I have this flow map here. Very important to sample it as non-color. Why? Because this flow map is a texture that contains data and we don't want to break that data with a gamma correction. Gamma correction is only for textures that contain actual color that is going to be displayed. Flow maps don't. Flow maps contain data that is going to be used to push the UVs. Therefore, we have to get the data as it is, linearly, without alterations, not non-color. Okay, so we have the flow map here. So what we are going to do is to achieve this effect first. I have this texture and I have this slider. So we are going to move this slider manually to push the UVs along the path that is defined in the flow map in either one way or the other. Okay, just because we have to start from something very simple. Okay, so to understand this, we take our flow map, which is this, and then we need to do something very important, which is unpacking our flow map. What I mean is that, if you remember, we just said that when the flow map is created, we have to do something that is basically this, taking the directions regardless on the angle they point to, including negative directions, okay, including the quadrants marked here with the crosses, with the X. And we need to compress this into a smaller space that goes from 0 to 1. Why? Because colors in textures only accept values from 0 to 1. And now, yes, we are going to pretend that 0.5 is our new center. We already talked about that before. But now, if we need the direction in the shader, we actually want the original one, the one that is not packed, the full range version of the direction. So if we said that in order to convert this direction into packed space, we did this operation to shrink the vector to the half by multiplying by 0.5, and then we moved it to the side by adding 0.5 on each of the axes. That means that if we want the opposite result, the backwards operation, then we need to just do the following. We just need to subtract 0.5 to the vector and then scale it by 2. And we can visualize this better in Desmos. Actually, if we go here, what I have here is actually a packed vector that turns around 360, okay? And we want to convert this into the full range from -1 to 1 again. So if we do these same operations that we have in the shader, which are basically these ones, now I have a vector which name is U for unpacked. I take the point, which is this point, the packed point, subtract 0.5 in both axes, and then multiply by 2. Then I have this new dot around, this new black dot. And if I display it with a line and I display a circle around, now we see that yes, it is now the original direction based on the packed vector. So what we have here is the flow map, the vector, the direction that comes from the flow map, and what we have here is the actual real direction unpacked, and the one that we are going to use to move our UVs. So let's do that. We have the unpacked vector. Now we see a different tonality of colors, and yes, now we see a lot of black color in the zones that don't move at all, because if they don't move, that means that they are 0, therefore they are black. So makes sense, everything is making sense. But there is a thing, these offsets might be too intense or too low, depending on what we are doing, but now we need a way to intensify these directions or make them weaker. So for that is just a simple scale, a simple multiplication. So we take our direction and we just multiply them by a number. Let's say 0.5, 0.1, 0.2, 0.3, etc. We can either go further than 1, or we can go backwards and invert the direction. So this way we can control how intense or weak is our offset. And now we need to use this to push the UVs. So what I have here is a set of UVs, something that we don't know. We are used to see this all the time. And we have the vector. So we already said that in order to make something to offset, to flow, we need to take the UVs and add some values in either the horizontal or vertical axis. Well, instead of doing that with a fixed value, we are going to do that with the directions that come from here. So that means that we only have to take the UVs and add our vectors from here. This causes that our UVs are now displaced, are now moved in direction of what our flow map dictates. And that means that we can now use these UVs to sample any texture. In this case, this grid texture here. So to put it like in perspective, I'm going to reset this to 0. So we have the flow map. We unpack to get the real rotations, the real directions, better said. We use those directions in a multiply operation, a scale operation, just to make them stronger or weaker or to invert them. And then we use that to be applied on top of our UVs, and we use those UVs to sample a texture. So that's the principle. However, you will notice that if we go very far, like if we intensify this like too much, the effect breaks. Now we have this ugly texture broken, and we need to do something for this. So that's the second part of the effect, and that's what we are going to see now. Excellent. So we say that we cannot just do this offset because at some point it's going to break. We need something to disguise this break. We need something to give the illusion of endless looping. And that's what we are going to see now in this example. So to understand it better, let's not focus in the shader for now. Let's just focus in this. And if I zoom it enough, we can see that it's actually two textures, a texture A and a texture B. Both textures are going in the same way, but the difference is that one of them is offset in time. Better said, one of them is ahead in time half of the way. So at the moment that the texture A is just starting, the texture B is already half of the way ahead. At the moment that the texture A is now half of the way, the texture B already reached its end and will go back to the beginning. So that's the idea. That's the gist of what we are going to do in order to achieve this flowing endless effect. But let's see it better in Desmos. So if we go back to Desmos, I added these two lines on top and the bottom. Basically, they represent the staging of our textures. In the top part, we have the texture A and texture B in the bottom part. They progress to the same place. They start from the same place, which is this axis, and they reach the same exact place, which is the dot line on the right side. But one of them is always half the way ahead from the other. And also, we have another thing. This ball that bounces from one texture to the other. This tiny ball represents a value that will help us to switch from one texture to the other depending on the stage. So the trick is this. Both textures are going to progress to the same place, are going to start like moving to the same goal. As we said, one of them ahead in time, half the way ahead in time. but we are going to have a mixer value, a ping pong mixer value that will help us to interpolate from one texture to the other. So when the texture A is on its beginning or end, because it's exactly the looping point, the mixer is going to look at that texture entirely. But at the moment that this texture starts going away, then the mixer is going to start putting more attention in the incoming B texture. So basically we have a value that is going to look in one texture or the other more and more depending on the staging. So let's go back to the shader to make things have more sense. So what we have here is exactly the same shader as before. We have the flow map texture. We have also the unpacking of the vectors. We have also the attenuation or intensification of the vector. And for now, let's just bring this vector down here and put it on this place. We are going to go back to it in a bit. But for now, let's focus in creating these elements, the texture A timer and the texture B timer, and also our mixer. Okay, so here I have a time. Basically, we have the time that increases endlessly from 0 to, well, whatever amount of frames we have in our project. And if you see, it starts growing from 0 endlessly. But we need something that loops, that cycles. So that's why we can take the time and just pass it through a fraction. A fraction, if you don't remember what is it, is basically a modulo 1 operation. And a modulo is the remaining value after doing a division. In other words, a practical use case of a modulo is to loop values inside of a certain range. And actually what this is doing is that it takes the time increases from 0 to infinite, but this loop controller constrains it to be eternally cycled from 0 to 1. So at the moment that the time reaches the value of 1, it resets it back to 0. So the value starts growing from 0, 0.1, 0.2, 0.3, 0.4, etc., 0.9, 1, and it goes back to 0. So that's the gist. And we can use this value to actually create these three things. Okay? So how we do that? Well, actually, the fraction is already a value that grows from 0 to 1. So that means that we already have one of them. We can say that is the texture A timer because it goes from 0 and reaches 1. But now, in order to create another timer for the texture B, which needs to be half the way ahead in time, well, if we say that the full range of this thing is 1, then the half of 1 is 0.5, meaning that in order to make the second timer half the way ahead from the other, we just need to add 0.5. And that's what we do here. We add 0.5 and we add another fraction to prevent it to surpass the number 1. So we just tell it, okay, you are ahead, but remember that you need to stay inside of the range of 0 to 1 and loop inside of it. So now we have both timers. We have the timer A and the timer B. And if I display these two, that is what I'm doing right now, they look exactly the same. It's hard to compare, but let's compare them in a more interesting way. Literally, we can use my custom node, compare A versus B, and put the input A in the A pin, B in the B pin, and now we are able to compare both timers left to right. I mean, compared on the left and the right side. So both behave exactly the same, but of course one of them is half the way ahead from the other. The same thing that we have been saying for these two timers here in Desmos. Okay, so now let's offset, let's start applying these like values to intensify our movements. So remember when we said that we put on hold here our vector, which comes from all this logic of extraction that we already saw? Well, we already see that these vectors can be applied to the UVs, right? But we need to attenuate them first. We need to make them stronger or weaker, as we said before. Instead of using a slider as we did before, now we are going to use the timers. So when the timer is 0, our directions are going to be basically nothing, no movement. The texture is going to be entirely reset. But at the moment that this timer starts to grow, the movement is going to be more and more and more until it reaches a maximum and then goes back to 0. That's the idea. So if we take the directions and multiply the directions by the timer, now we see how the directions scale increase based on the time, meaning that if we use this to move our UVs, they are going to offset until they reach a certain point and they are going to be reset back to 0. Okay, so that being said, we can do that same thing for the timer B. So we have these two sets of growing vectors through time. Again, it's better if we compare them with the custom node that I made. So if we put these two vectors, we can see that it's basically the same flow map that is growing based on time, but one ahead on time from the other. One of them is ahead in time half the way from the other. We are going to say that a lot, but it's very important. So we are ready to apply these offsets to our UVs. For now, I'm going to disable this scale. I'm going to explain why I have that in a bit. But yeah, the thing is that we have our UVs, as we saw before. We have something that moves those UVs. How we do that? Again, we just add. We take the UVs and add the vector. Okay? So this means that we can already use these UVs to sample a texture, in this case the texture A, which in this case, just because it's a very tiny texture, needs a bit of tiling, and that's why I added this scale of 20. But yeah, now we have the texture moving. However, if you pay attention, you will see how it resets very hard, and we don't want that. But first, let's finish connecting this setup. We do that for the texture A with all these values that come from the timer A, and same thing for the timer B, using the texture B. But the logic is exactly the same for both parts. Okay? So now, if we take both textures A and B and pass them through a mix, now we can use this slider to choose between one of them. Like, I can choose A, I can choose B, I can choose A, I can choose B, etc. Or something in between, right? But what if we replace this slider with something else that is dynamic? Of course, we can use this mixer to act as value for that slider. So now you catch the idea. It's like this mixer is going to tell this value to move from one texture to the other depending on the timing on the stages. So let's see how we calculate that value first. So if we focus in this one, we have a behavior of bouncing. We have a ping pong thing. I think that goes to 1 and goes back to 0 and 1 and 0. It is not smooth, it's hard, it bounces hard. It is a zigzag basically. So for that we can take the fraction that we already grabbed our loop controller, which again goes from 0 to 1 eternally and repeats. We can multiply that by 2, we can subtract 1, and we can get an absolute value. But why? Why does this make sense? Well, let's visualize it in Desmos. So if I go here, we can see that this is our fraction value that goes eternally from 0 to 1 in cycles. Okay? So now if we apply this operation that is multiplying by 2, we can see how now it's just like bigger, but it's the same behavior, just bigger. Okay, makes sense for now. Now let's subtract 1. We do that here. Now it is the same behavior, but it's mirrored now. Well, not mirror, it's like it's on the middle of the x-axis. So if we apply the final step, which is an absolute value, that means that all the parts that are here in negative space are going to just be flipped. They are going to be reflected upwards. And that's what it happens. We achieve a ping pong behavior, a zigzag behavior by doing these 3 operations with our cycle fraction value. Let's visualize it. So we have a thing that grows from 0 to 1 and goes back to 0 and bounces to 1 eternally, right? The difference with this one is that this goes from 1 directly to 0, but this other value doesn't. This value reaches 1 and then starts walking backwards until it reaches 0. So if we use this as replacement of this mix that we said before, then we achieve the full effect. Let's do that. You see? There you go. Now you have something that... sorry for that. Okay. You have something that resets our... not reset, sorry. We have something that switches between one texture or the other, depending on the timing. On the right timing to make it smooth, to disguise the fact that they are resetting hard behind. So this is the second part of the effect, but we can still do something more interesting with it. And that's the next thing that we are going to see. Okay, finally, how can we achieve something like this where we have the flow map and also we have another material that represents all the static zones that don't move at all? Similar to what we have with the lava, where all the surfaces that don't move are actually solid rock and the lava is the only thing that moves. Well, we can achieve this with exactly the same shader that we have with an extra step. But before, let's see what we have here in this shader. In this shader, we have basically everything that we have seen already. We have the flow map, we have the unpacking, we have the attenuations, we have all the time stuff and the looping controller and the timers A and B. We already talked about that. Also, we have the application of these flow vectors intensified by time into our textures, into our UVs to sample a texture, etc. We already saw that. But now everything merges into this mix, right? So this mix represents the final output of our flow map shader, regardless of what it is, if it's lava or water or slime or whatever. And now we have another texture that represents a different material. In this case, well, this checkerboard. So now we need something that helps us to mix these two together, because if we put the flow map material that we have here in the static material, let's say it that way, both in a mixed node, and we start controlling the factor from one side to the other, then, well, of course we can switch from one to the other, right? But what if we, instead of controlling this manually with this slider, what if there is a way to actually tell it on which places of the texture it is actually moving and use that as controller for this slider? And that is exactly what we are going to do. So all the shader that you see here is exactly the same as we saw before, except for this part. So in this part, what actually happens is that we are taking our unpacked vectors from here, and vectors have intensities, they have lengths. So of course all the vectors that are here in the dark zones have 0 length, no movement. And the vectors that are actually colored, they are they actually have some length. Can be tiny, very tiny here, for example, but it's bigger in the middle. Okay, and we can make usage of that length directly as mask, as replacement of this slider. So if we use that length as replacement of this slider, sorry, like that, then we have something like this. Let's do that. Length, we take it and we use it as a replacement. Now we have something like this that is almost there. Almost there, because if you focus enough in the flow part, you can see that we still see both textures at the same time, and probably we don't want that. Probably we want to be one material only. And of course, gradually switch from one to the other, but at the end we want like 100% one material or the other on the strongest parts of the flow, right? Okay, so let's try to do that. For that, let's take the length as we have it and let's just power it. Why? Because the power is going to make all the tiny lengths to just grow a bit, but the bigger lengths are going to be escalated exponentially, causing it to grow its thickness, to create an effect of growing thickness. Of course, it is limited to where the actual vectors stop having a length. So it cannot grow more than that. But it's fine because we can just tune the flow map to have the thickness from there if we want. But this is just like an extra control in the shader, okay? So if we apply a power to our length, now we can say that we can control the thickness. But now what if we want to control the hardness? Because right now the thickness is good, but if we focus here, we have a big ramp between the black and the white. Probably we want to make this harder, and for that we can rely on this, an addition that's going to make all these values that are almost there to reach the white to just escalate one step above, just to go a bit further and reach the needed value. That's why we just add something, this value. But of course, if we do that directly, that means that also the darker zones are going to grow. So we don't want all these zones in black to grow, and that's what is happening. If we start increasing this value, that's what happens. So to constrain all these zones back to the black color, well, just multiply everything by the original length. So any vector that grows undesirably, like here, is going to be clamped or sent back to black because it's multiplied by 0 by black. And that's it basically, because now we can control not only the thickness but also the hardness. We can make the gradient hard. So let's, I went too high. I'm going to put this in 0.5. Okay. So let's connect this final thing. We can call it path mask. And let's connect this final thing as replacement of the slider that we saved. And there is it. Well, right now it looks exactly the same, but let's play with the values. So let's increment the thickness a bit. And let's increment the lift a bit. You see how now it is harder? Actually, yes, everything is clamped. So we are preventing everything to surpass the number 1, which is fine. So there is it now. We have all the pieces to understand the shader of the lava, which in a sense is exactly the same thing that we have been doing. But I'm going to skim it very fast because for real, the technique that we just saw is exactly the same there in that shader. It's only a bit bigger, that's it. So let's finally see that so we can go back to the tool and start breaking it down. Finally, let's see how all the stuff that we just saw makes sense in the actual lava and rock materials. So what I have here is this setup. Basically, Remember that we just saw that all this shader relies on a lot of mixes. Basically, we use a mix to switch from one version of the texture to the other that is offset in time half the way. And also we used another mix to differentiate between one material and the other, in this case rock and lava. Well, the only difference here is that instead of a simple mix, we have this big thing that is a big mix in a sense, nothing else. If we look at it inside, it is just a bunch of different mixes, ones for each channel of our PBR material. And if we need more properties, of course we can implement them. Nothing stops us to do that. And what we have here, well, we have a mixture for the color, for the metallic, for the roughness, for the index of refraction, and the normal map of one material and the other. Also, we have emission color and emission strength, because the lava needs a bit of emission. But it's at the end a mixture, that's it. Okay, so let's see what we have on this side. Well, before that, everything after it's mixed ends up connected in the same PBR principal BSDF material. So we don't actually have two different shaders, it's actually the same shader. We are just combining the different values for color, metallic, etc. So this means that we can develop each material, the rock and the lava, separately without needing to make them know each other, which makes the thing way more cleaner. So the rock material is actually a very simple thing. Inside of it, it is just a bunch of textures for color. Actually, here is an ambient occlusion, but I'm not really using it. Well, yes, I'm using it. I'm multiplying it, yes. Yeah, that's not important. The thing is that the output of this, it's only based in some textures that, well, I grab online, basically. And they are basically this. We have a rock texture. We have an, actually let me just display them in the image editor. So we have, let's say, this texture for the color, we have this texture for the normal map, and this texture for the, what is this, roughness, etc. And you can find any texture out there and you can use your own. That's another story. But yeah, the part of the rock is not big science, it's just that. Okay, so let's get out of here. The thing is that the material of the rock just outputs everything, and this goes to the first element of our mix. Okay, same thing for the lava. We are going to see what is inside of it in a bit, but yeah, for now we can just assume or care about the outputs. It's a color, it is a metallic, well, it has no metallic at all. Inside of it is probably hard-coded to 0. I don't remember. We are going to see that in a bit. We have roughness 0, almost 0. I don't know. Let's see. It's better to visualize it this way in linear. I think it's, well, it's not 0. It's gray. Okay. We have the normal map. We have the emission. We have the emission strength. So we are going to see what is inside of it in a bit, but at the end we have this big mix, basically, that again we have this value that goes from 0 to choose one of the materials. Let's say, let's focus on the color. What's going on? Yeah. Let's focus on the color. Let's visualize the color. So we have the color of the rock, and if we move the mix, now we have the color of the lava, which are using the same texture, but yeah, it's a different color. It could be a different texture if you want. Same for the, let's say, the normal map. Well, the normal map is also the same thing, but let's say the, I don't know, the roughness. Yeah, the roughness changes a bit, but yeah, let's focus on the color that is the most evident. The thing is that for both materials, I'm actually recycling the same textures. I'm just like playing with the color inside, so that's why it wasn't too obvious, but yeah, that's what's going on there. And everything mixes at the end with the same principle BSDF. But the difference is that instead of using this slider ourselves, we use this, the flow path mask that we just created before. So let's connect this first here, and let's connect the entire shader again. Okay. So now let's see what is inside of the lava material. In the lava material, we also have a big mix, but for this case, it is for mixing the lava textures that are in the different versions ahead in time. So this is basically the lava that flows in the timer A and the lava that flows in the timer B. Again, we can compare this with the same node that we did before. Compare A versus B. And if I put this both together, one side to the other, we can see that yes, they are the same texture, but one of them is half the way ahead in time. Basically what we just learned. We are not going to repeat that. Before of this, all the logic, all the shader that we did for the flow map is actually here. We have the flow map, the full range conversion, the path mask, the intensification, the timers, the ping pong mixer, the loop controller, etc. We have everything, but we packed everything in a node that is easy to use and that we can paste on any shader. And in this reader, that is how I called it, we have as output the texture, the UVs, basically the UVs for the texture offset number 1 or the texture offset A, and the UVs for the texture offset B. Again, compare A to B. Whoop. I can put this here, and by playing it's a bit smooth, but yeah, we can see how one of the sides pops before the other, or yeah. So nothing that we don't know already. But the difference is that instead of reading a flow map texture, I'm reading this, an attribute that comes from the actual geometry. This is actually our flow map generated by the spline, and we are going to talk about that in a bit. But it's, at the end, the same concept. Remember that at the beginning I told you, it doesn't matter from where the flow map comes, as long as the data is correctly represented as colors. The directions are correctly represented as colors. So that's the only thing that we care about, and that's what's happening here. We are grabbing the information of the flow map not from a texture, but instead from the actual geometry written by our spline. So now we are ready to understand the breakdown of the tool. Okay, we can start breaking it down. So now we have all the concept that we need regarding the flow maps. Of course, we will need a bit of context in geometry nodes, but you can learn that everywhere. So let's begin. Yes, the tool is made in geometry nodes. What we have here, we have all this graph that it's basically the tool split in different steps that are completely agnostic from each other. This is great because this will allow us to understand every single piece without mixing everything together. So let's see what's going on. Basically, all this problem is solved in 6 steps plus a final step that is just setting up some stuff for the output. Okay, so what happens here is this. First of all, in the input, we have a surface, which is the owner of the tool. Basically, this surface is the plane. Or if we were working with this other example, this surface would be this other plane, or the cylinder, right? So in this case, the surface would be the cylinder. So that's basically the surface. Let's go back to this other one. Okay, let's select it again. Then we have 2 inputs of splines. Why? Because one input is actually direct geometry, the other input is a collection. So here's the thing. This tool can be actually used in both ways. You can attach it as modifier, and if you do so, that means that you need to assign your splines, as we said before, as a collection. When you do that, all those splines are going to come from here. But also, nothing stops you to, instead of using the tool as a modifier, using it as another geometry node inside of a bigger graph. And if you do that, well, you might have some splines in your graph and you can inject them with the other pin. We are going to see an example of that at the very end. But for now, both pins contain splines in different ways of input, but both are splines. Then we have the values that we already saw, that is the subdivision and the invert flow direction. And basically that's it, right? Actually, we have a bit more properties, but we are going to make usage of them later in the logic, not right here. Perfect. So what's the immediate next step? We already said that all this workflow relies on the resolution of the geometry, because at the end, all this data is stored in the actual vertices of the geometry. That means that the more geometry we have, the more resolution our flow map has. So when we go here and start subdividing, actually, you know what? I'm going to, this plane is actually pre-subdivided, so I'm going to just delete all the subdivisions with a limit dissolve. Sorry for that, but yeah, we have a plane now. And then we go to the subdivision and start adding more and more and more vertices. And the more vertices we add, the more resolution, of course. We already talked about that. Right, so that happens here. Very simple. What's the next step? The next step is this. The trick to write the flow map is the following. We are going to grab the surfaces. We are going to grab the vertices, better said, the vertices of our splines that are closer to the vertices of our geometry. So, in other words, these vertices here, actually let me just put it like this way. These vertices here are going to get the points from the spline that are here, the closest ones. So for example, if we use the pencil, this vertex here, let me just change the color of this thing. This vertex here is going to grab the vertex of the spline that is here. This, sorry for that. This vertex here is going to grab this vertex from the spline here because it's the closest. And it doesn't matter how far it is. It's always grabbing the closest vertex, even if it's inside of what is visibly moving or not. We are going to see how this is handled later. But yeah, every single vertex in the geometry is going to grab the closest point in the spline. Again, final example. This vertex here is going to grab the vertex from the spline that is here, the closest one. Okay, so what is next? I'm going to delete this node for now. That being said, let's switch to the material again. That being said, we can go to the step 1, which is process the spline tangents. So let's see what is inside of it. What happens here is that we receive our splines either as geometry directly or from a collection. Doesn't matter. We extract them regardless of where they come from, and we just combine everything. Why? Because it's easier to just manipulate all the splines together. In this case, we only have one because it's easier to demonstrate. But if we look at the spreadsheet, we see that yes, in fact, our geometry contains one spline, and we can see all the points of that spline. But if you notice, this spline has too few points. They are not enough points for us to do a decent flow map. So we need to give it more resolution. And in order to do that, we have to use the realized instances because we want to actually affect the spline, and we cannot edit instances in geometry nodes. We have to realize them first. So that's why we convert them into a real thing that we can individually interact and modify. That's why we realize the spline first, and then we sample the curve with way more points here. You see? And yeah, we can see everything in the spreadsheet, but what if we just convert this to curve to points, let's say, just to visualize it better, like this, and change the mode from count to evaluated. Of course, these points are too heavy, it's too big, so let's just scale them. I think it's radius. No, it's not that. Point radius. Excellent. So now we see how the spline is full of points, a good resolution of points. So this way, when the surface tries to grab the closest spline point, it's going to always find a nice one. It's going to always find a good resolution to grab the closest one without artifacts of proximity. Nice, we can delete this for now. So what's next? We need to grab the curve tangent. So if we grab the splines, look what happens. If you grab the splines and grab this node curve tangent and visualize it, you see all these like gradient that goes from red, from yellow and green. And does this look familiar? They look like our flow map, more or less, right? Because they are just vectors represented as colors in the spline. Of course, these are vectors on the spline. They are not flow mapped yet, but the conversion is almost there. Perfect. So let's disable the viewer for now. So what happens if we just take those directions and multiply them by -1, right? And choose between the original or the one that is multiplied by -1 based on a toggle. So if we do this, we are basically just switching the direction of the spline, which is what we have with this toggle here in the tool UI, which comes from the input that we have out here. Perfect. So next step is let's give it a name, because yes, we have this vector, we know that is a direction, but later on we are going to forget what is it. It's good to always assign names to things to know what we are doing. So we just use a store name attribute. We just store what we have here and just give it a name, spline tangent, because the spline tangent is actually the direction that touches the spline on every place. So basically, if we have this spline, this is a tangent, this is a tangent, this is a tangent, this is another tangent, etc. so on. And these tangents are basically almost what we want to make our flow map. Perfect. So let's go back here. Let's just give it a name. If we see the spreadsheet down, we can see that yes, we have a column now with a vector on each element showing a tangent, a vector, a direction basically. Excellent. And this is what we are seeing here as colors. Finally, just because we are going to see that later on it's going to be easier for us to interact with the spline, not as an actual spline, but as an actual like thin mesh. Let's just convert that to a mesh. That's it. Unfortunately, on meshes in geometry nodes, once they are meshes, we cannot continue visualizing attributes on very thin things, but the values are still there and we can confirm that in the spreadsheet. So if we go here to the mesh and the vertices, we see that our spline tangent remains there. The only difference is that now we cannot visualize it. Probably they fix that later, but it's just an artifact of geometry. I don't know, it's probably just because it works like that behind. I don't know the explanation, but the thing is that we cannot do that. So for now, we will have to rely on the spreadsheet. That's what it's intended for. So let's go to the next step. Here we already have the tangents, the splines processed, meaning that this output has as geometry a lot of points, a lot of vertices that are over the spline, and each point has a tangent, a direction that tells us on which direction the spline was looking at each place. Good, okay. So now what we have to do is to use this data and transfer that data to the vertices of the plane. So we need to transfer these splines into this geometry, basically the geometry of the surface of the lava. So now we have to do what we said at the beginning. We have to tell each vertex which point on the spline is the closest one and grab the tangent from there. So that's going to happen in the next step. So let's enter to step 2, which is transfer spline tangents to vertices of the surface, a very literal name. So let's enter there. What do we have here? Well, basically, we said that we want to write data on the surface. That's why we take the surface and write an attribute on it. In this case, the spline tangent. The spline tangent was in the spline before. Now we are transferring to the actual geometry. And what we are transferring? Well, the closest one. That's why first we are getting the nearest index of the spline. So what it happens here is that probably it doesn't make too much sense visualized in this way. Let's reduce the resolution just a bit. Okay, so what we are seeing here is the surface grabbing the index of the closest point of the spline. But it's going to be better to visualize it this way. If you go to the corner here, I think it's here, and enable attribute to text, you will see that now every vertex has a number, which is basically the index of the closest point. So for example, this vertex here that says 27, it's super tiny, but it says 27. It means that the closest point from the spline is the point number 27 for this vertex. Or let's say another example, this one that is way closer. This vertex here from the surface has the number 43, meaning that the point from the spline that is closer is the number 43. So that's what is going on here. Let's disable the attribute text for now. So we are stealing, we are grabbing, we are querying which is the closest point, and we are using that to sample a value from that spline using the closest point. Meaning that, yes, we ask the spline, hey, which is the closest point to me? Okay, I'm going to grab a value from you. That's what's happening. And which value? Well, the spline tangent. So here we have the spline tangent that, remember that we can unfortunately not visualize directly in the spline now that it's converted to a mesh, but it's here in the table. So once we just flip it, because it turns out that we need to invert it, but for the user, the sense of direction, it makes sense for them. It's just an internal thing that actually when we do a flow in direction to the right side, actually we are moving stuff, the UVs to the left side internally, but for the user that doesn't make sense. So it's just a matter of UX. We are just inverting that vector just because of that. And then we normalize. Why? Actually, you know what? This normalize is not necessary technically, because every tangent that comes from a spline is already normalized. For now, I'm just going to leave it as it is. So yes, that's the value that we are stealing from the spline. Basically, we are saying, hey, spline, which is the closest point to me? Okay, give me your tangent. That's what is happening. And now we can actually visualize it. If we connect the surface to the viewer and visualize the value that was grabbed from it, now we have this thing, which is super ugly, but it makes sense because these colors are directions from the spline. And when we subdivide this more and more, let's do that, it's going to make more sense. It's a bit more cleaner. You see how it starts like doing more or less the spiral? It is not yet there, but it's more or less starting to resemble to something in the shape of the spiral. The problem here is that we are not seeing the full spiral because every single vertex in the geometry is actually grabbing a value. For example, all the vertices here are also grabbing values from the splines, and we don't want that. We want only the closest points to grab a value. So let's do that now. Just before of that, you see how all this is like a bit jagged, an artifact. This is just because of the resolution. Of course, the more resolution we have, the smoother this is going to be. But we can just use a blur attribute. And finally, we store it in an attribute with a name. Because again, it's always good to name things to understand what we are doing. Perfect. So let's go to the next step, that is only allowing the vertices that are very close to the spline to actually grab a value from the spline. So for that, what we are going to do is the next thing, step 3. Get proximity of vertices to the spline. And we are going to use this proximity as decision, as limitator for our vertices to grab or not, to be able to grab or not information from the spline. So let's see what is going on here. Let's see what we have here inside. Sorry for the cut, I made a mistake in the previous recording, so now I'm correcting, but yeah, we are actually inside of the step 3. Okay, so what we are going to store here is the actual distance for each vertex of the surface to the closest point on the spline. Okay, so what is going to happen here at the end is this. We have this plane, we have, let's say, this vertex here, and this vertex is going to get the distance to the closest spline. Now, literally, the distance here and here, or for this vertex we're going to get the distance to this vertex. Let me just paint this in another color. Oh, I need something that makes more contrast. Well, probably this way is more evident, but yeah, basically that's what we are getting. Why? Because that distance will help us to actually allow the vertices to grab the directions from the spline or not, if they are far enough. Only if they are close enough, they are going to be permitted to grab the information from the spline. Perfect. So for that, to get a distance, we need 2 things: positions. So if we have 2 points, like point A and point B, and we want to get the distance, of course we need to know where point A and point B are, right? So first of all, we need to know where the closest point from the spline is for every vertex of the surface. And in the similar way that we did before, we ask which is the index of the closest point of the spline for every vertex. So let's say that for the vertex 32, the closest vertex of the spline is the vertex 10. Okay, that value is going to come here, and then we can use that value to sample, to ask the spline another value, in this case the position. So what is happening here is that every vertex say, hey spline, which is your closest point to me? Okay, it's this one. Okay, give me the position of that point. That's what is happening here. So we can visualize that in this way. We can grab the surface, we can grab the sample index, and we get this weird mask that also resembles like a spiral, but it's not quite there yet. This is only the positions of the closest points on the spline. But to get a distance now, we need another position, which is the position of the vertex itself. And that's, well, basically retrieved with just a position node. So what we are seeing here is the actual positions of the vertices, right? And it makes sense because to the right you have the reds, x-axis, to the up you have the greens, the y-axis, and the combination in diagonal, etc. But these are the actual positions of the points. And if you get the distance between the positions of the points and the positions of the closest points in the spline, well, if you want that, just do a distance between both. And now you have a path mask. And you can use this to allow the vertices to actually grab values from the spline or not. This is what decides if a point is allowed to grab information from the spline or not. Of course, this is inverted because what we want is to allow the closest vertices to actually retrieve information and to avoid the farthest vertices to grab information. So we just need to invert this thing. To invert it, we just do this calculation. We just clamp it and we just divide it by a thickness, because this is actually normalizing the value. So for example, if you have a value that can go from 0 to 10, right? And you have another value that is 5, and you want to normalize the 5, right? If you want to normalize, so it's now 0.5 and goes from 0 to 1, you have to divide it by its maximum, right? So if you have 0, well, 0 over 0, I know that it doesn't make sense, but if you do that in geometry notes, it's going to give you 0. Or if you do like 10 over 10, 1, but 5 over 10 is going to be 0.5. So now your value is normalized just by dividing it by the maximum range. By doing that, now you are able to control the thickness. Perfect. And now we can use this. Now we can invert it. Now we have to invert it because yes, we need the white to be here, because white is like the multiplier that will respect the actual values retrieved from the spline. A 0 value, a black value, is going to just push whatever value it grabs to 0 in a multiplication after. So let's just invert that. What we want is actually here, this. So white means whatever value I grab from the spline, respect it. Gray means whatever value I grab from the spline, well, just take a bit. And black means whatever value I grab from the spline, ignore it entirely. Of course, we also have the jagged attribute just because of the resolution of the mesh, but a blur attribute operation fixes it as before. Perfect. So now we have all the pieces that we need to actually get the directions only on the right place. And that's the next step. Let's go out of it. Step 4. Attenuate tangents based on proximity. So basically, all the mesh entirely is actually retrieving tangents directions from the spline. But now, we only want to allow the vertices close enough to do so. So for that, what if we just take the surface, the spline tangents that we already had, all the vertices have retrieved spline tangents from before, but just multiply that by something that kills them on the zones that are not close enough by our path mask. So just do that, and now you have directions that are not flow mapped yet. They are still in 3D, but they are almost there. Now you have directions in 3D space, but only close to the spline. Perfect. And one more time, naming things help us to make things cleaner and to understand what we are doing. So if we visualize this geometry, we will see that our spline tangent is now saved here with the final value that comes from the spline, and also attenuated based on the proximity. Excellent. So next step. The thing is that if we do this, it might work, but it's only going to work if we do like a 2D flat flow map in a plane. But at the moment that we want to do something like this, everything is going to break. Why? Because the 3D space coordinates or the 3D space vectors directions from the spline only makes sense if they are perfectly aligned in 2D space, meaning only makes sense on planes. But for this kind of situations, we need to convert them from the 3D space into the 2D UV space. That process is called TBN conversion. Tangent space conversion also is both names are valid. So let's see what happens there. Let's go back to the plane. Convert tangents to UV space. Step 5. Excellent. So again, we have the surface that already comes with all the data that it needs, the spline tangent and the path mask. Okay, but now we need to do something very interesting, and is the UV TBN conversion. So basically what we are going to do here, it's quite tricky if you don't know matrices, but a simple way to see it is this way. Have you ever worked with matrices in game engines where you have like these functions like invert transform, for example, where you have a coordinate in one space and you can convert it to be relative to another space? For example, when you have something attached to a player or something, let's say a gun or something, and you drop it in the ground, now you have to detach it from the space of the player and just drop it in world space, or vice versa. Well, that happens with matrix operations, with inverse transform operations. Okay, and that's basically what we are going to do. We are going to grab the coordinates in 3D space of the splines, and we are going to just make them relative to the UV flat 2D space. Okay, so what I have here is this operation UBTBN. Okay, I'm going to give the details about this later. Probably I can do another video on this because it's a bit more complex, but in short words, what it's doing is the following. It is actually, we can change to the other example of the cube, for example. Where is the cube? Where is the cube? Where is the cube? Here. What it's doing is the next thing. For every vertex, it is creating like a set of different vectors. It is creating like a space, a coordinate system. For example, here it creates one, here it creates another one, like this. Well, a bit ugly, but that's the gist. Okay, again, I can create another one here. Excellent. And these spaces, these coordinate systems are aligned to the UVs. So for example, for this one, the direction X of the UVs will flow in this direction. Okay, regardless of the direction the flow map goes, that's another story. We are talking about only the direction on which the UVs face on. So for this vertex, the UVs on X will flow on this side. But probably for this other one, probably is not here. Probably is here. So probably for this other space, the UVs flow on this side for the X. And probably for this one, it's this other side. So let's complete this thing. So probably now we have Y on this axis, Y on this axis, and Y on this axis. And of course, the last one is Z, right? So what it's going to do is that it's going to grab the directions that come from our spline, for example, this one, and it's going to put it to move this vector to the space that we define on the vertex. So now, to demonstrate it with another color, I'm going to add another color here. I'm going to put it like probably, let's say something like purple. Excellent. So let's say that you have the spline and it grabs this tangent from here. Okay. So what it's going to do is to grab this vector and put it here, put it in this space. let's say this way, and it's going to push it down. It's going to push it down to the X and Y axis. So that way it is getting rid of the coordinate Z. It is basically just projecting, just stealing what it needs. It's like just pushing downwards the vector that it finds above of it, and it's pushing it down to its surface and representing that vector in 2D space. Same for here. So for example, if we have the curve here and it has this vector, this direction flowing this way, it's going to say, okay, give me this vector, please push this in this space, and it's going to project it only in the X and Z axis. That's a good analogy to understand what is going on. Unfortunately, going more deeper would need a whole context into matrices, but I can do the video after. But yeah, this is a very, very nice and enough way to visualize that, to visualize what is going on. Okay, so for now, let's delete all these drawings. Let's go back here to the step 5. In that projection that we just mentioned, all that step that pushes down the tangents from the spline into the UV space are actually happening here. The invert matrix, which is what we are used to use in game engines, like the inverse transform whenever we drop a gun from a player, whenever we want to attach something to another object. That's basically what we do in game engines. The only difference is that in Blender, instead of using a transform, we use a matrix, but it behaves in a very similar way. And instead of using inverse transform function, we use invert matrix function. Okay? So with this transformation, basically we take the tangent and we just transform it to that space. We are saying, hey, spline tangent, I know that you live in 3D space. But you know what? I'm going to transform you into the space of 2D UV. That's what's happening. Of course, of whatever vector comes as result from here, we don't care about the Z-axis. Okay, that's what we said. We are just pushing down the vector and we are ignoring entirely the Z-axis. So that's what we are doing here. Just dot pass it. Just keep whatever is projected and just get rid of the Z-axis. And again, store it with a name, because names always allows us to know what we are doing. So that's basically almost there, because if you visualize this and visualize this attribute, you see now, well, I know that it's probably not looking too pretty, but it makes sense internally. All these directions are actually unpacked vectors in UV space already. Let's see if by any chance in the other example it looks more pretty, but yeah, you see here it looks more like what we would have in a texture flow map. Actually, it's going to finish making sense if we visualize that here. You see, this is more similar to what we saw in the unpacked flow map before. Excellent, so we are getting out of time, so let's go a bit more faster. After that, let's just smooth the thing. So we already have the spline tangents projected in UV space. Okay, let's just pass that through a blur. So what we have here is the final blurred thing. More smooth, more hard. But this is a very trivial calculation. I mean, the hard part, the tricky part already happened. Again, we just blur the thing and store it again in the spline tangent attribute. And finally, we just need to store our result flow map with a name. For that, we just open this and we just translate the spline tangent that makes sense here in our tool. But for the user that uses this data in the shader, probably we should choose a better name, a clearer name, and that's why we just store it with a different name. That's it. Flow map raw and flow map texture, which are basically two versions of what? Of this. Basically, the tool automatically injects to the shader these two versions that we saw at the beginning during the theory of the flow maps. So we can grab whatever we prefer. If we prefer to grab the pack and go for a more standardized option, there you go, just unpack it on your shader. But if you want to be more practical and you already know what you are doing, well, probably it's just better to use the full range version. Yeah, I probably didn't choose the better names, but that's the idea. After all, whenever we do a store name attribute, all these columns of data are actually already available in the shaders. So you can go back now to the material and remember the part in the lava shader where we use this flow map reader. We already saw what is this, but remember that now we weren't using a texture. Well, that's because we were reading it from here, from an attribute node with exactly the same name that the tool delivers here, which is this thing. So that's basically it. That's basically all the theory of the breakdown. Of course, we can go way more deeper. I actually would like to go way deeper in the matrix part where I explain the TBN, and I will do so. I just need to do that in a different video because it's a bit more complex and it requires a bit more background. But I'm sure that with the explanation that we did for that part is enough for you to properly work and have some progress. Also, that step, if you think about it, might be optional for you. Finally, let's see a simpler version of this tool, and is this. If you assign the minimalist version of the geometry node tool, well, everything is summarized in this. That's it. And what we have here, well, we have all the curve to mesh thing, and we steal the curve tangent, but then we just multiply that tangent by the path mask, basically the same thing that we did of stealing the position of the closest point and having the direction and using the distance, and using the distance to allow certain vertices to have more contribution or less contribution, etc. All that story is basically this. But the only thing is that this simplified version only works if you have a plane and is perfectly aligned with the 3D space of the tangents. That's it.